Hello everybody, I'm Simon Rowell. I'm the meteorologist for the British Sailing Team. And what I'm going to talk about today is atmospheric stability, how that affects us and how we can work out what it is. Right, I'm just going to share my screen and then hopefully we shall have some slides to illustrate things. Right, there we go. So, stability, the atmospheric kind. What is it and why do we care? First of all, let's have a look at what actually is stability. Now, what I've got here is the blue blob down on the surface there is a parcel of air that's cooler than the air around it. So what that means is that if for some reason this parcel of air gets bumped up, say it's part of an onshore wind and it goes over a hill or something like that, then what will happen is it will rise up, but because it's colder and therefore more dense than the air around it, it'll fall back down to surface. So that is stable airflow, generally cooler airflow. Neutral airflow, which is quite rare to actually find, means that the parcel of air is the same temperature as the air around it. So if it's bumped up, then it'll go there and it'll just stop. It'll stay there. So that doesn't happen that often. What happens more often than that, however, is if you have unstable air. So in this situation, the air is warmer than the air around it for some reason. Perhaps it's gone over a warmer patch of water, or if it's over land, maybe it's gone over a large urban area with lots of warm concrete around buildings, things like that. And basically, as that starts to rise, it'll continue to rise until it is stopped by something being warmer than it. So that's unstable air. And when you have unstable air, you have lots more mixing involved, vertical mixing. So how does the surface affect the wind? Well, what tends to happen is that if we have our surface here and we have our general wind flow, in this case from the left to the right of the screen, that wind flow that's directly above the surface is called the boundary layer, and that's the layer of the atmosphere which is directly affected by friction with the Earth's surface. So that can be that varies in depth depending on the temperature of the surface that it's flowing over. So in the UK, on a cold winter's night, it could be as low as 150 meters. On a warm summer's day, it could be as high as 15 to 1800 meters. So very variable depending on the temperature of the surface that's going over. Generally, the boundary layer that's where you find your first clouds. Or whatever the lowest clouds are, they happen at the top of the boundary layer normally. And above the boundary layer, that's where you have wind which is unaffected by the surface, and that's called geostrophic or sometimes gradient wind. So that's the wind which is basically described by the synoptic charts, and that's the stuff that's whizzing along unaffected by surface friction. So the boundary layer, as it moves along, it's not a uniform layer. There's lots of mixing and bumbling around inside it, and it depends really on how the surface is heating up underneath it. As the surface heats up, air rises. So as your flow is going along from left to right on this image, you'll have circulation going along with that. And it could be big ones, it could be small ones down the surface, and occasionally you'll have large ones which will go all the way up to the top of the boundary layer. And occasionally what will happen is that they'll actually break through the boundary layer if you have a particularly warm patch of air, because it'll have momentum as it goes up, so it'll burst through. It can get entangled in the faster moving air above it, which I've got represented here as that blue blob moving along from left to right. So what will happen is that faster moving parcel of air will get entrained, it'll get wrapped around by the stuff that's about to fall down, and it'll make its way down to surface with very chaotic mixing around as it goes, and it'll hit the surface, and that's what gives us our gusts at surface. So as you can see, the boundary layer itself, the bit that we go sailing in, can be quite chaotic. And the first thing that you'll probably start to associate with stability is the way that, especially on a slightly cooler morning, to start off with, there's often very little wind at all, and you'll hear the phrase, "Well, we'll just wait until it mixes down." And as the morning gets warmer, then the surface does get warmer, and the air gets warmer, and you have a lot more mixing happening. So, as that instability increases, then you do start to get stronger winds mixing their way down to the surface to give you decent sailing wind later on in the morning. So. This is all great. As those of you who've listened to me before know, I can get very excited about all things meteorological, but why do we care? So let's have a look first of all at vertical wind shear, because this starts to explain why we care. What I've got here, this graph here, the vertical axis is altitude, so going from the surface through the top of the boundary layer and up above there, and then the red curve represents wind speed, increasing from pretty much zero right at the surface, and then increasing with altitude. Now, the example I've got here shows a stable atmosphere, so there's not much mixing around, which means that the wind at the surface is a lot, or just above the surface where your sail would be, is a lot less than the wind above it at the top of the boundary layer. This difference in wind speed is called wind shear. So if people talk about how there being a lot of wind shear, that means that there's a lot more wind up top than there is down below, and that's generally the sign of a stable atmosphere. With an unstable atmosphere, you have lots of mixing going on, and so there is still the surface wind will still be less than the wind up above it, but it quite quickly, quite rapidly increases in speed. So if you went from, say, there, for example, 100 meters, and then went up to 400 or 500 meters up there, your wind speed would be pretty much the same. So this is an unstable atmosphere with lots of vertical mixing, and in those you tend to have much less wind shear. And this does make a difference to your sail. If we now look at the same graph, but look all the way down, just at what's happening on your mast, so the 4 to 8 meters of your mast, depending on what you're sailing, on a very cool, light wind, stable day, you can have a big difference between the wind at the surface and the wind at the top of the sail, both in wind speed and in direction. Sometimes you can have a 15 to 20 degree direction shift in your wind, and in the northern hemisphere anyway, the wind up top, the faster wind, always comes from the right of the wind at the surface, and it's the other way around in the southern hemisphere. So what this means is that if you're sitting sailing your dinghy, say, and your head is at about a meter or so above the water, then your head, your ears, your nose, your physical senses are basically your wind instrument, and they will be telling you there's not much wind at all. But at the top of your sail, there could be another 3, 4, 5 knots of breeze up there, just in that short distance. It does happen. So what that will do to you effectively, that means you'll think you've only got, say, 4 knots of breeze. But in fact, at the top of your sail, you'll have more than that. So the wind will actually feel heavy. And this, I think, is, in my opinion, this is where the old thing that in winter, when things are colder, people say, well, the wind's heavier. No, it's colder. Yeah, I don't think it is. I read the numbers once. I can't remember the details, but I do remember that the difference in pressure caused by the air being slightly more dense, because it was at, say, 5 degrees Celsius as compared to 20, is only a couple of percent, or maybe 5% tops. It's not really that significant, whereas this effect is. If the wind is unstable, if it's well mixed, then the wind down at the bottom of your mast will be much the same. It won't be that different to the wind at the top of your mast. And also the direction difference won't be as much. So this means that you'll have a far more even wind spread up your sail. And that actually makes a big difference to the way you trim your sail. So if we take a really extreme example of stable air, if it's a relatively cold morning and it's quite light wind, so a light, cold breeze just dribbling down over the water, what you'll find is that the wind at the bottom of the sail will be, say, that direction, given by the blue arrows there. So you'll trim the bottom of your sail, the boom, that way. Whereas the wind coming from the top of the sail will be significantly to the right, maybe 15 degrees to the right of that. So you'll have an awful lot of twist in your sail. That's great if you're on starboard tack. But however, as soon as you tack across when you're on port tack, the wind is still the same, but your actual sail trim is a whole lot is nowhere near as efficient, because you can't get the twist going the other way. You can't twist to windward. So that means that what you may well find is that in very stable air, your starboard tack setup will be a whole lot more efficient than your port tack setup. If it's unstable, there's less twist, and so much less difference between your port and your starboard tacks. Now, I must emphasize that this most of the time this isn't that obvious an effect, and is quite often overcome by or overshadowed by other things, like, for example, swell direction, and the way the waves are hitting the boat, that sort of thing. But it can be quite important in cold, light wind scenarios. Excuse me. So that's what happens on a boat scale. Can you look at the forecast and think, well, is it going to be stable or unstable? Yes, you can. The low pressure systems are generally unstable systems. They on the synoptic chart, we're used to seeing the wind spiraling into the middle of the low pressure system, and when it goes into the middle, it's got to go somewhere. So it goes up. It goes up and then diverges at the top of the low pressure system. So you have air rising pretty much all the way through your low pressure system. What I have here, on the slide here, is looking at a low pressure system from the side, sort of a slice through. So if you're over here on the right, if you're in the relatively cold and dry air ahead of your low pressure, ahead of your warm front, then it'll be fairly dry, so not very humid. Therefore, your visibility is going to be great, but you're still going to get some clouds. You're still going to get little puffy bits of fair weather cumulus, some low scraps around. So you will still the air still will be to a certain extent unstable and reasonably well mixed. As this warm front approaches, you get the normal progression of clouds. The light wispy ones up top, getting thicker and deeper as you go down. Now, when you get to the warm front itself, you may have some showers coming down. They will give you a different type of instability. There'll be more of it. Basically, clouds are a really good indicator of instability, because all a cloud is, it's a collection of water droplets held up by air going upwards underneath it. That's how they work. So the bigger the cloud is, the more air you've got going up underneath it, and basically the more unstable things are. Once the front has gone past, then you're in the warm sector here, and you're probably underneath stratus or broken stratus cloud, that very homogeneous layer cloud, quite low sometimes. Your conditions can be quite steady. The wind speed is maybe not going up and down that much. Your wind direction maybe not going left or right that much, but it's still an unstable situation, because you have your cloud there, which means you must have air going up to keep the cloud up there. But what you can tell is, because your cloud itself is fairly uniform, the way that the patterns of air go up and down underneath it will also be fairly uniform. So you'll tend to find bigger, lazier pressure patches which don't move as fast underneath your stratus cloud, but it's still unstable, so you still get a decent mixing through the atmosphere. Your cumulonimbus cloud, of the cold front, that tends to be way more unstable, and that makes sense. The bigger the cloud, the more air's got to go up to hold it all up there. So you burst through that and then get into the nicer stuff behind. But basically, your low pressure system is an unstable system. The opposite of that, of course, is a high pressure system, which is almost by definition a stable system. What happens with a high is that you get air subsiding from above. And often this air will have started off down in the tropics. It'll be on the other side of the North Atlantic High, for example. So you'll have your air coming in from the tropics and subsiding down towards the surface. What happens down at the surface is the sun's radiation, the ultraviolet radiation, gets absorbed by the surface, be it land or water, and then re-radiated as infrared radiation, which warms up the lowest boundary layer part of the atmosphere. So you get convection and all that good stuff. However, because the air subsiding from the top started off in the tropics, by the time it gets down to there again, it'll have warmed up enough so it'll actually be warmer than the air coming up beneath it. So that acts as a lid on the whole system, and is called an inversion, which is a term you've probably heard. And what you'll also see generally with an inversion is especially in summer when things are a bit warmer, there's a thin layer of broken, hazy, very thin stratus. And also you'll find that there's, over land, there'll be a very dusty layer, and over water that's more hazy with moisture instead. If you pinged up a weather balloon and you recorded the temperature, then the temperature would decrease, because temperature does decrease as you go higher, up until that inversion. Then there'd be a step up, and you'd see the temperature start to decrease again there. And that has a big implication for how the air behaves at the surface. If you have an air parcel there which gets heated up, then yep, it'll rise up, but it'll find that to get to the inversion, it won't be able to go any further. Until, of course, during the morning, the infrared radiation being chucked out by the Earth's surface warms up that lower boundary layer, and so the temperature of that whole layer increases until it matches the temperature of the layer above it. And at that point, your inversion, your inversion is gone, and your air can move up. Your air can move up unimpeded through there. What you also find at that point is that your visibility at surface gets a whole lot better too, which it's a whole lot more pleasant sailing. But generally, high pressure systems therefore are more stable. Right. There's also a concept which is very useful, which is it's not an official one, this, but I like to make a difference between your vertical movement and your horizontal movement. Your vertical movement, your mixing is defined by the stability, as we've just seen. And when I talk about steadiness, I like to talk about the way that your wind moves from left to right. So you can have if the wind direction isn't changing very much, for me that's a steady wind. So you could have a stable and a steady wind, and the sea breeze normally fills that definition quite nicely. So its direction is pretty steady, and it's not very well mixed, so you don't have very big gust to lull difference. So that's a stable and a steady wind. You can have an unstable but still steady wind, and what that is the direction is pretty much the same the whole way through, but there's a much bigger difference between the gust and the lull. Now, a good example of that would be a gradient wind coming offshore, coming over flat, quite hot land, then getting onto the sea, because the direction would be fairly steady, but because it's going over a hot and increasingly hot during the day surface, you'll have much more vertical mixing. So you'll have gusts coming down, and it'll be all much more chaotic. You can have a stable but an unsteady wind. That's quite unusual, though. What that would be a cold airflow coming off land, but going through or around obstacles. So it's a cold airflow, so it's not very well mixed, so it's stable. But if it's going through a couple of different valleys, if the wind direction just upwind changes a little bit, maybe it can change and go down a different valley this time. So you'll have what are seemingly random left to right shifts in your fairly stable wind flow. That's really quite unusual, and we tend not to get that very often around the UK. What is a whole lot more usual, though, is to have it unstable and unsteady. This is when you have wind coming over a hot surface, so it's very well mixed and quite gusty. And if you have it trying to go through or round obstacles, valleys, mountains, that sort of thing, if you have a slight change in the direction of the wind, upwind of these obstacles, then it can maybe flick around the other side of the obstacle, which happened a lot, for example, in the Rio Olympics with Sugarloaf. Or it can go down a different valley or that sort of thing. So what you end up with is big shifts left and right, seemingly at random, and also quite a big gust to lull difference. So let's just have a quick look at a couple of examples of this. First of all, we've got, this is an example of a steady and unstable wind. This is the Levanta, the east to east-southeast wind, which blows through Cadiz, which the river sailing team has used as a winter training venue over the years. And this is a nice example because all the land upwind of the bay here it's quite dry, it's quite arid, so it gets hot really quickly in the morning. And if you look at a wind trace on one particular day, I mean, it's February, so it's midwinter, and it wasn't actually that hot, but the warmth of the sun did increase the temperature of the land. Still, we start off quite early in the morning at about 10 o'clock. The red curve is direction, the blue curve is wind speed. And you can see the direction curve there. It goes up, it goes left to right a bit, but nothing dramatic, maybe 10 degrees each way. And it's fairly steady until about midday when it starts to get very funky. So it's still fairly steady all the way through there. Whereas if we look at the wind speed, each one of these vertical units there is 3 knots. So we're already getting about a 6 knot gust to lull difference, which on a mean wind speed of 18 knots is pretty significant. But then as soon as you start to get to late morning, so 11:30, noon there, we start to get gusts to lulls of 9 to even 10 knots. And that's a massive difference between the top end wind and the bottom end wind. So this is a really nice example of steady and increasingly unstable wind there. And in the afternoon, it just got completely nuts. Anyway, that's a different story. Here's a good example of another offshore wind, gradient-driven wind. This is summer in Weymouth a few years back. And the thing which I want to show here really is the difference in cloud. The wind direction, it was, again, red is direction, blue is wind speed. The wind direction, on average, was fairly steady all day, about 060, so just east of northeast. But you can see the difference in the clouds from 10 o'clock in the morning to 1 o'clock in the afternoon is quite significant. Still, excuse me, little fluffy cumulus clouds, but a whole lot more of them as the land got warmer underneath them. So that's an indication that the surface that your wind is moving over is getting hotter and hotter, and so your wind is getting more and more unstable. And you can see that it started from about midday. It's midday there. You can see that it started to go left and right a lot more, so becoming less steady. And also the gust to lull is increasing through the early afternoon as well. That's from 16 all the way down to about 7 knots. That's getting quite unsteady and quite unstable there. So a nice example again of your instability and your unsteadiness increasing with surface heating. Another good example of unstable and very unsteady in this case. This is Marseille, which is the sailing venue for the Paris 24 Olympics. Now the forecast wind here was for the wind to come over and around this rocky peninsula there, which has lots of quite steep peaks and deep valleys in it. So lots of opportunities for the wind to go around one way or around another. And also at the top end of it here, which you can't quite see on the image, there's a big valley there. So with just a little bit of wind change there, the wind can start pouring in from that way as opposed to going around there. And if we look at the wind trace from the wind surface that day, again, red is direction and blue is wind speed. Even in the morning, even early on, in the afternoon, 1 o'clock, we still got 20 to 30 degree shifts. And then when things get really hot, which is normally about 2 o'clock in the afternoon, 2:30 in the afternoon, we've got wind going. The wind goes left to right massively there. Now that's not because the wind's out to sea is doing that. It's because the wind going through the obstacles trying to get to the race course. Sometimes it goes through that one, sometimes it goes through that one. And that's reflected as well in the gust to lull ratio there, or gust to lull difference. The wind isn't that strong on this day. It's only 6 or 7 knots on average. And you can see that there's a lull down to 3 knots, a gust up to 8 knots there. That's a really big gust to lull difference with that mean wind speed. Let's move on to something more stable. This is a sea breeze forecast for the bay in Palma. And what was supposed to happen here that day was an offshore breeze, probably about 060 in the morning, with then a sea breeze making its way into the bay during the afternoon, like that. So we should have an unstable offshore gradient wind to start, gradient-driven wind, and a stable sea breeze coming in the afternoon. And that's exactly what we got. In the morning here, you can see that, again, red is direction. So the unstable offshore wind in the morning, anywhere from 050 to 100. So really big shifts left and right. So unsteady as well as unstable, massive gust to lull difference. Then the sea breeze kicking in quite nicely about 1 o'clock and being very steady on the direction after that. Really nice and fairly stable, not too much of a gust to lull at all. Maybe 2 to 3 knots on an 11-knot wind speed after that. So a really nice example of the change in the characteristic of the wind from morning to afternoon. And this is probably the nicest example of a stable and a steady sea breeze I've got. This is from Weymouth back in 2015. The red is the wind direction, and you can see that it's only going left and right by about 5 degrees. It's wonderful. And the blue is the wind speed, and on a mean wind speed of about 14, 15 knots, you've got a gust to lull difference of maybe 2 to 3 knots. That's about as good as it gets. So what we've seen so far, and we're nearly finished, is the difference that the surface temperature and the physical nature of the surface make to, first of all, the stability and the mixing, and then the steadiness of the breeze as well. Just one last thing before we finish up is as the wind comes offshore, if you have an offshore breeze, not only do you have the difference in heating between, say, the land and the sea, but also you've got the difference in surface friction as well. There's less surface friction over water between the surface and the air than there is over land, which makes sense. So what you do find in the northern hemisphere with an offshore breeze, the wind does bend to the right as it goes offshore by about 15 degrees or so, and how quickly that happens depends very much on the temperature of the land and the sea. If everything's nice and warm in the summer, if you've got a warm land, relatively warm sea, and little puffy cumulus clouds everywhere, then you'll get that bending happening within about a kilometre of the shore. Whereas in winter, when you've got a relatively warm but still not exactly tropical sea and a very cold land, that same effect happens, but it takes a while for the faster air to mix down, because of course this air coming off the land is itself cold, so it needs to be warmed by the sea, which is only relatively warm, not actually warm. So that bending to the right will take about 5 kilometers in winter. So that may be in summer, that may be something that will actually help you if you're inshore. Unless it may not happen quick enough for it really to affect you on a particular beat if it's happening in winter. So just to sum up here, stability is all about surface temperature. So have a think about what type of surface it is and what temperature it is that the air is blowing over. And changes in that surface temperature from one type of surface to the other will cause a change in surface stability. Clouds give you a clue. The pattern of the clouds is directly related to the pattern of the air rising and falling. So that's directly related to gust patterns and whether you've got big lazy patches or small little puffy ones. So have a look at the clouds. They tell you lots of good things. And on a big picture point of view, low pressure systems are generally unstable, highs are more stable. Well, that's it for this afternoon. Thank you very much for listening, and enjoy your sailing. If you do have any questions or comments, do please send them in. You can send them in to the British Sailing Team's Twitter or email or Facebook accounts. Any questions we get, we will answer. Enjoy your sailing. Good luck.